order containing the terms zeta square, eta square and all that. And we can also map curved boundaries in such cases. So then we have studied 9-noded and 8-noded quadrilaterals and 6-noded quadratic triangle we have studied now. So once this serendipity family has been studied now, today I would like to enter into a new topic which is called as axisymmetric elements and axisymmetric loading. So the topic name is axisymmetric solids. Axisymmetric solids subjected to axisymmetric loading. Okay. Now, what is the meaning of this? See, in our day-to-day engineering applications, we find many equipments which are what you can say axisymmetric. For example, if you take a cylindrical vessel, it may be a boiler, it may be a pressure vessel, it may be a gun barrel, it may be a thick cylinder, thin cylinder, any type of you can say solids of revolution we call it, or the shape of the maybe the equipment or the container may be in the form of a frustum of a cone or cone itself, and it may be in the form of a spherical ball, the huge what you can say petrol tanks and all that. They are generally in chemical industries and all that. These are huge spherical vessels are made to store large quantity of fluids, and in such cases when the loads are acting, how exactly the stresses and strains and other parameters, maybe sometimes they are subjected to thermal stresses also. So in such cases, how to analyze such things? See, when you look at this, these are, as the name itself indicates, these are solids of revolution we call it. That means by revolving a 2D plane around a vertical axis or a horizontal axis, when they are rotated about an axis, here we get the required solids of revolution. So the interesting part here is, since the loading and the geometry is symmetrical about one of the axes, let's say a vertical axis, Z axis we call it, and the revolution axis we call it as R axis. Generally we can talk it as RZ plane, and the rotation we consider it as theta, the rotation of the, you can say the plane. When it is rotated around Z axis, we get the cylindrical object. For example, just to show you, look here, if I take one rectangular element like this, and this is my what is called as Z axis, and if I rotate it by an angle theta in this plane, this plane is called R plane, you can say. So what we get is, this is going to be a solid of revolution like this. This is going to generate what you call it as the cylindrical surface. You are going to get this. You can see here, this is how you are going to get this, and you will get this like this. See, this is the, you can say plane. It is a 2D plane. It is a rectangular 2D plane, and it has been rotated about the Z axis, and it has generated the required solid surface, and this is what we are generating. So generally we have what are called as Z axis and R axis and theta, rotational theta. But interestingly, since because of the symmetry, this type of solids of revolutions can be treated as two-dimensional elements only. For example, the stresses and strains are going to act only in the RZ plane only. It can be considered as a simple ordinary plane, and the stresses are going to remain everywhere around the theta. So therefore, these three-dimensional problems are generally converted into, axisymmetric problems are converted into two-dimensional analysis, and then we are going to do that. For example, if you take maybe a rotational flywheel, you are interested to analyze a rotating flywheel. For example, this is the, see obviously this is the rotating, means this is the N with which it is rotating. This is the Z axis and this is your R axis, you can say. So here, if I consider the self weight of this, it is going to act in the Z direction. Say, let us say WZ is the load which is going to act in this. And since it is rotating, the mass of the rim will have what is called as a centrifugal stress or centrifugal force, and this is going to act in the R plane. So therefore, this type of problems can be handled very easily by considering them as two-dimensional problems. So now let us quickly see how exactly we can formulate the required equations and all that. For that, first I would like to make some interesting sketches, and then we will go for the real analysis of this. This is the distributed on the circle. This is the pressure or whatever you can say acting inside, and this is going to access. Let this small thing is going to be called as this one, and this is the rotational angle. This is theta. If I show it in the two-dimensional axis, the same figure, I can just show it in the two-dimensional figure. See here, I can find out the pressure distribution from inside. This is the pressure distribution all along the length of the edge of this particular thing. Here we can find out some distribution of the load also here also. This is also load. A point load can act here at a given point Pi, and this, as usual, we consider a small elemental area dA, and the displacements in this particular case is U and W. U, V, W when we are talking about. In this plane it is U and W. So I can just have this. I can show that this is the cross section of the element, and this particular is nothing but the boundary L, we can say. And this is your R axis, this is your Z axis, what you can say. This is the traction which is acting on the inner surface of this thing. This is the revolving area. See, this load is acting at I. This is called revolving area A. This is the revolving area A. This is elemental area dA. This is one interesting point what you can note it down. And if you want another small element of this, when I consider, you can see here, this comes here like this, this is like this. This is your Z axis, and this is the radius at R. This is acting. This is called dr. This is the cross-sectional area what just now I have showed you. I just hatch this. This is the angular portion what I have considered. Let us say d theta, small angular portion slice I have taken. And naturally the length of the arc is radius, and r theta means this is r d theta. This is the and this particular, you can say, volume of this whole element is dV. So this volume, elemental volume dV is given by R d theta dr into dz, or already you know R d theta dr into dz. This is of course dz now. This is the height dz. This dr into dz is the dA, the elemental area of the cross section. That is whatever is there here. This is about this. And when you look at the, you can say, the displacements and all that, U, it is going to be U and W in this case. The displacements are also going to be two components. Traction, when I say here, it is going to be TR and TZ. There is no X and Y, so we get in this form. Similarly, body force, if I want, it is FR and FZ transpose. Then the point load, when I say PI, it is also a vector. These are also going to be in the form of Px and Py. Okay, this is what we will consider. Here also can take them as Fx and Fy. So these are, of course, all these are going to be RZ components only. Here, like that. Okay, fine. See, this is about what I wanted to tell you about the figure of the axisymmetric solid. It may be anything. It may be cylindrical. It may be in the form of a frustum of a cone, or it may be any other like flywheel and all that. We can take circular. So it's nothing but what is called as solids of revolution. So here the basic equation for the strain energy, when we want to write the total potential energy of this equation, we will first start with axisymmetric formulation. First let us start with total potential energy, because as I told you, since it is independent of the rotation of the theta, how to modify the equation we'll see. Now the potential energy can be written as, see, the potential energy pi I want to write. So pi is equal to summation 0 to 2 pi, because the rotational angle we have to take. Then the next comes over the area. This is strain energy is going to be this one into dA into d theta minus, this is that expression for the strain energy. Now we will go for the force vectors. All these definitely will come into 0 to 2 pi, and this is again over the volume will be converted into your area. This is dA into d theta. Then about the traction. See, traction is also going to be 0 to 2 theta, but in this case it is 0 to L. There is varies between 0 to L. Okay, or you can say over the length, you can find out. This is U transpose T R dl d theta. This is about the traction force, and the last point load is always going to be the summation of all the vectors Ui transpose Pi. See, this is going to be the total equation for potential energy. Since I told you that this equation is independent of theta, I can take out that 2 pi. Directly I can write that 0 to 2 pi will come as 2 pi only, because 0 to 2 pi d theta is nothing but 2 pi minus 0. So therefore, this will come half integration sigma transpose epsilon r dA minus integration over area U transpose F R dA minus over the length L U transpose T R dl. See, these are all involving the integration part, and minus this is independent. This is I ui transpose pi. This is nothing to do with this. All these terms are common, so that's why we are going to write them in all together like this. This strain energy part has been already written, and this is going to be the total equation. See, now you don't find any theta. This is independent of this theta. So with the help of this, now I can start developing the remaining part. Okay. Now, when it comes to strain, here in the 2D plane, what we had seen in our earlier case, there were only three components, that is epsilon x, epsilon y, and gamma xy. That is two normal strains and one shear strain was there. But in the present case, in the case of axisymmetric solids, we also get one more component of strain, which is called as epsilon theta. That is in the direction of the rotation, we get that. So let us see how exactly we can formulate that and how to write the strain and stress components here. Of course, here C matrix, material characteristic matrix, is also going to be different here like this. So now let us quickly note down the strain component. Strain epsilon in this case is epsilon r, epsilon z, gamma r z, and epsilon theta transpose. Okay, fine. So to justify this particular relation, I wanted to show you the drawing. This is the this after the displacement, this element will move to the new position. Like here, this is the new position of this element in the given r direction. This is your r direction. It is moving by u here, whereas here this is having a little more than that. That is u plus dou u by dou r into dr. This is the incremental length here. This is, of course, as I told you, this is your r. So obviously this is r d theta, this one. But when it comes to this, it is r plus u now. So therefore r plus u d theta, this particular thing. That is, there is a change in the length of the member. That is, the length of the arc has been changed. And if you look at the normal plane, that is ZR plane, what we call it. If I call this as R versus Z here, the original, what you can say, original element, let us say this and this, if I take like this was originally a rectangle initially before the deformation. Now after the deformation, it has gone to new shape. Like this. This is the new shape. So naturally, we need to find out what are the changes here. This, of course, Z displacement is, as I told you, this along the Z direction, this is dz. I have already told you. Along the radial direction, this is dr. This is our dr. The total displacement of this corner from here to here is u. This is the displacement. And if you look at the vertical displacement here, it is dw. Vertically, this point is correspondingly moving both in r direction and z direction. So therefore, this will be this is u and this is dw. Whereas here it is w plus dou w by dou r into dr. That is going to be the displacement of the other node. Like from here, it has reached to this point. This is the element what we are going to take. Similarly here, when you see here, what is this? U plus dou u by dou z, because this point from here to here you have moved in the direction, so therefore this is dou u upon dou z into dz. This is what you are going to get this. And similarly, if you want from this corner to this corner, whatever is traveled here, this distance, okay? This is what is this? W plus dou w upon dou z into dz. This is the vertical displacement of this point. So this is the original and deformed shape of the element after the loads have been applied. So now let us quickly write how to write the strain components now here. See, in this case, strain is like nothing but epsilon r, epsilon z, gamma rz and epsilon theta. If you want to write it in terms of the partial derivatives, it will be written as dou u by dou r, dou w by dou z, dou w by dou r plus. This is going to be dou u by dou z plus dou w by dou r. But there is one more epsilon component, E theta is there, that is nothing but simply u r by r. So these are the corresponding partial derivatives of the strain components. So this we are going to write down that. And when we want to find out the stress, of course stress is also going to be 4 by 1 only. This is how this is going to be 4 by 1. Here also you will get sigma r, sigma z, tau rz, and what is this next? Sigma theta. Yes, this is the transpose. These are the 4 components you are going to get. And as I have already told you, the stress and the strain are connected by this. Since it is 4 by 1, this is also 4 by 1. Obviously, this is going to be 4 by 4. See, it is on the earlier case for CST elements and all that when we were talking about the material matrix C was of 3 by 3 for plane stress as well as for plane strain. But now we have to find out for axisymmetric solids. So directly I will give you the what is the value of that. C for axisymmetric solid, sometimes they will ask you in the examination. It is given by E into 1 minus nu, 1 plus nu, 1 minus 2 nu into bracket 1 nu upon 1 minus nu, 0 nu upon 1 minus nu, 1 upon nu upon 1 minus nu, 1 0 nu upon 1 minus nu, 0 0 1 minus 2 nu upon 2 into bracket 1 minus nu, then 0 nu upon 1 minus nu, nu upon 1 minus nu, this is 0 and this is 1. See here, this is going to be a 4 by 4 matrix. So when this is multiplied to the strain components, what you are going to get is the stress component. That is all this 4 components of stress, you are going to get this. Okay. So this is how we are going to relate stress and strain. Now let us see how we can make finite element modeling and how to make the discretization and how to generate the given equation. See, again, as I told you, it will be simply considered as a 2D element only. Like for example, if you are using constant strain triangular element, it will be treated as like 2D element only, but there is a rotation. This rotation is in the theta direction, so that will take care of the 3-dimensional solids of revolution. It is nothing but a shell. When you rotate it in the form of a ring, you will get that when it is rotated about z axis. So now quickly wrote down how to make the finite element modeling with the triangular element. See, look at this. This is I am doing this with the help of what you can say the triangular element. Okay, these are all nodes. These are the corner nodes. We have start naming them. These are the common nodes which are sharing so many elements. You can see there. Okay, this is that. So let us note them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, then the 16, 17, then 18, 19, 20. So it means there are totally 20 nodes. I have discretized the same shell, what I had showed you in the earlier first figure. This thickness, complete thickness of the wall of the shell, that is solidus of revolution, I will convert this into a 2D. This is, always remember, there is axis here. This is there and this is going to be your R axis. This is R and this is Z. So I have taken this particular segment and I have divided that. Let us give the element number 1, 2, 3, 4. We will say fourth element. 5, 6, 7, 8. 5, 6, 7 and 8. 9, 10, 11, 12. Okay. 9, 10, 11, 12. 13, 14. This is 13, this is 14. 15, 16, 17, 18, 19, 20, 21 and 22 elements. So totally there are 22 elements with 20 nodes. You can see there. So this is what we call it as the finite element discretization of this element. So always remember the node numbers are having the same relation. Here I have used the same, you can say for the CST element, whatever is there, I have used that. This is going to be 2j minus 1 into 2j. So if you look at the layout, see for example, if I show you how exactly this looks. This is R and this is Z. See if I take this like this, and if I consider a triangular element, okay, I will consider this entire thing here now. See here, this I am considering like this. This is all dotted. See, this is the triangular element what I am using here now. Here, this is the triangular element, and this is the same thing. I can write it here now. This is again the same thing. It has been taken here. What I would like to tell you here is, though it is a triangular element, when it is rotated about z-axis, it will be forming the ring-shaped object, you can call it. So therefore, as far as our this is concerned, these are going to be, what you can say, this is, let us say, if I say 1, then the coordinates of are R1, Z1. If I write this R2, Z2, and if I write this as R3, number 3, then R3, Z3 are the, what you can say, the coordinates of this particular point. And you know that at any point, if you take, let us say, RZ, the displacements are U and W. This is the point what you have to always remember. And this is the triangle when you talk about this. The area of the triangle is, let us say, AE. AE is the area of the triangle. And if you take, as usual, you know that for a three-sided triangular element, there are 6 degrees of freedom. There are Q1, Q2, Q3, Q4, and Q5, and Q6. See, it is a CST triangle only with the 3 nodes and 6 degrees of freedom. That is 2 degrees of freedom per node. We are going to have this. So therefore, if I want to write the relation, just recall whatever I have done in the case of CST. We did that, it is NQ we had written, where U is nothing but now U comma W in this case, and the N was nothing but N1 0 0 N1, N2 0 0 N2, and N3 0 0 N3. This was the case what you have already studied that. And the nodal displacement at the element level, it consists of 6 degrees of freedom. That is Q2, Q3, Q4 and Q5 and Q6. Let us write it as a transpose because it is going to be a 6 by 1 matrix. So this is going to be 2 by 6. This is going to be 2 by 1. This is the matrix what you are going to get this. So this is how you are going to. And you are already knowing the values of the shape functions are what? N1 was zeta, N2 was eta, and N3 was 1 minus zeta minus eta. This is already, you are familiar with the shape functions, and we can start writing this. Yeah, now, if I recall that again, U was written what? N1 Q1 plus N2 Q3 plus N3 Q5, which is in this case zeta Q1 eta Q3 plus 1 minus zeta minus eta Q5, which can be written, and W is also same. What is W? It is now zeta Q2 eta Q4 plus 1 minus eta minus eta Q6. Okay. So these are the two components of the displacement, and if you want, you can rewrite the similar to x equal to n1 x1 plus n2 x2, like that we used to write. Since we are using the same isoparametric formulation, here also I can write R is equal to, what is R? N1 R1, that is zeta R1 plus eta R2 plus 1 minus zeta minus eta R3. I can write. Similarly, Z coordinate also you can write eta Z1, eta Z2 plus 1 minus eta minus eta Z3. Because these are because of the isometric formulation, I can just go on writing the same thing. So once we know this, suppose if I want the strain, so dou u by dou zeta, we are already knowing, and dou u by dou eta. If I want to find out this is going to be J matrix into dou W by dou u by dou R, dou u by dou Z. Okay, again this is called as the, what you can say, the Jacobian of the transformation. What is this J? Tell me. J is, if you rewrite that, it would be equal to dou u by dou zeta, dou W by dou zeta, dou u by dou eta, dou W by dou eta. See, this is going to be called as the Jacobian of transformation. So with the help of that, I can easily find out this. Okay, we will now move on to the next relation, that is, instead of dou u, now dou W, we will use the second relation. What is that? Tell me. Here only I can write dou W upon dou zeta, dou W upon dou eta. This is given by what? It is equal to J only into dou W by dou R, dou W by dou Z. But what, for finding the strain, what we require is on the other part. So naturally I have to find out this one. So if you recall, it was J was what it was in terms of x13 and y13, x23 and y23. So instead of that I will replace it by R and Z. These are going to be replaced by that. So automatically, if we want to find out the, you can say, inverse of this matrix, here also, what is the determinant of J? Which is equal to R13 into Z23 minus Z13 R23. Okay. With the help of this, I can find out the determinant of the Jacobian matrix, because ultimately, when I want to find out the real values, and this you are already knowing, the mod of determinant of J is always equal to 2 times the area of the element. We are already knowing. So this is another important relation which will be still valid in the case of axisymmetric solids also. So now let me find out what is the dou U by dou R what we need, and dou U by dou Z what we need from that figure. That is here. Like if you take the first one, obviously I have to take the J inverse of dou U by dou zeta and dou U by dou eta. This is one interesting thing. Similarly, if I want dou W by dou R, dou W by dou Z, if I want, what is that I have to take? It is again J inverse dou W upon dou zeta and dou W upon dou eta. What is this J inverse? Tell me. Inverse of a 2D this matrix, 1 upon determinant of J. What I have told you? These will be interchanged and they will remain there only with a negative sign. So it is Z23 minus Z13 minus R23 R13. So this is the, what you can say, J inverse of a matrix now. So if you substitute all these things, so let us now, come on, let us substitute all this, whatever we have found out in our epsilon matrix. Because I have already told you what is meant by epsilon matrix in the beginning only. I have told you. What are those? Just check that. Okay. Now let us quickly write there. See, once you substitute them in our epsilon matrix, what is that epsilon matrix? I have told you dou U by dou R, dou U by then dou W by dou Z, and then gamma H. Instead of gamma RZ, we have written other two, and then finally epsilon theta, what we got. So therefore, the strain matrix comes like this. Here, interesting point is 1 upon a determinant of J is not coming common, because last term epsilon theta is nothing but R by theta. So therefore, when you take this into account, this will come Z23 Q1 minus Q5 minus Z13 Q3 minus Q5. Similarly here, minus R23 Q2 minus Q6 plus R13 Q4 minus Q6. Whereas here, minus R23 Q1 minus Q5 plus R13 Q3 minus Q5 plus Z23 Q2 minus Q6 plus or minus Z13 Q4 minus Q6. Here, this is not the end. Still we have one more row. This is what is U by R. So it is N1, N2 Q3 plus N3 Q5 and divided by U by R. This is R. So therefore, this is going to be what we call it as the strain matrix. When you write this, all this in the form of a, let us say, if I write B equal to epsilon equal to B into Q matrix. If I write this, then we get where B is nothing but strain displacement matrix. I have already showed you this in almost right from one dimensional, two dimensional, everywhere I have showed you the relation between epsilon and the B matrix and Q matrix. That is what we have seen. So let me write the big expression for B matrix. For an axisymmetric element, we should know how exactly it is going to be considered. So therefore, let me write the B matrix. Here it comes. Z23 upon determinant of J 0 0 Z12 upon determinant of J 0 R21 upon determinant of J M3 upon R, and coming to the last one, 0 R21 upon determinant of J Z12 upon determinant of J and then J. This forms what we call it as the element strain displacement matrix. Okay. So if you want, you can write down where this B matrix, which is of what, 4 by 6. Okay. This is called element strain displacement matrix. Yes, this is what you need to find out. And later on, once you have established this strain relation, it is easy to find out the stress, and then we can go for the derivation of the element stiffness matrix and all other details as such. Now let us quickly see how exactly we can write down the total potential energy equation, and out of that, how I can find out the, let's say, element stiffness matrix and other details. We can see there now. Okay. So let us write a potential energy approach. We'll go for potential energy approach. First, let me write the total potential energy. TPE, we can total potential energy pi is given by, what is the equation? Tell me. Summation over the elements half into bracket 2 pi epsilon. I will substitute, you can say sigma as epsilon transpose epsilon, and this one into R dA minus 2 pi integration over the element Q transpose F R dA minus 2 pi integration over the element Q transpose T into R dl. So this ends the integral part of that. The last part is your point loads, that is Ui transpose Pi. Okay, like U1, P1 like that. Suppose you have Px and Py like that, how it is there? It's like Pr, P theta components are there. That need to be multiplied here. UV, and this is UW, and this is PR P theta. I hope you understood. This product is nothing but UR, what is this? U into PR plus W into PZ. This is the meaning of this, because the components are PR and PZ in the R direction and PZ direction, and the corresponding displacements are U and W. Therefore, this will represent the total potential energy equation. But out of this, if you take only this part, this is nothing but the strain energy part. Okay, this is nothing but strain energy. So therefore, element strain energy, if I take, what is this vector will be? UE is given by half, you can call it as half. This 2 pi will go outside. It will not come into picture in this case. Directly I will write half, and you are already knowing epsilon is equal to, or you can write like this, equal to Q transpose B transpose, and epsilon is equal to BQ. So if I substitute that directly into this, what I will get is Q transpose into bracket 2 pi will come inside over the element. This is P transpose C into B into R dA whole bracket into Q. So this is very much similar to what you used to write. What is this? Q transpose element stiffness matrix into Q. Here, this is what. So the meaning is, whatever is there in this bracket, this is representing the element stiffness matrix. So if we know how to integrate this equation, so I can find out that. That is, therefore, my element stiffness matrix KE is to be written as 2 pi integration over the element B transpose C into B into R into dA. Yeah, this is the most interesting part of what you have seen. See, if you look at the B part, that is the strain displacement matrix, when you see the fourth column of that you have seen, it is containing terms like N1 upon R, N2 upon R, N3 upon R, and all that. So that means we need to integrate this equation at a given R. So additionally, this R, it means where exactly that value of R is what? It is not neither at R1 or R2 or R3. That R need to be integrated with respect to certain value. So therefore, B, when I write the fourth term, are always integrated at the B and R. These are integrated at the centroid of the triangle. Please remember, at the centroid of the triangle, not at any other point and all that. It is always we are taking. So therefore, if we take at the centroid of the triangle, you should know the property at the centroid of the triangle. What we know? N1 is equal to N2 is equal to N3, which is equal to 1 by 3. This is it. And then we need to find out the centroidal radius, which is R1 plus R2 plus R3 upon 3. So where R bar is called as the radius of the centroid, you can say. So therefore, when you calculate with the help of this at the centroid, we write instead of B matrix, I will write it as B dash. B bar means this is the B matrix evaluated at the centroid of the triangle. Because you just cannot integrate at any R. R has to be at a particular point. So therefore, we are taking this. So therefore, our modified this element stiffness matrix will be KE is going to be 2 pi R P transpose into C into B bar into integration over dA. This is the over element. And this integration over the element is nothing but the area of the element only. So therefore, what I can get is 2 pi R B transpose C into B into, here itself you can add it, area of the element will come into picture, 2 pi R into AE. This is what I can write down. So this is giving you the element stiffness matrix, and you are already knowing the element area of the element, which can be directly obtained by half of the determinant of J. This you have already established this relation. From this you can directly find out the, you can say area of the element, and you can find out that. Otherwise, if you want at any other point, then you have to find out R has to be found out by this relation. Okay. So this need to be found out at this given positions like that. So it depends upon where exactly we are going to evaluate our element stiffness matrix. So that depends upon, if on an average we take it as the centroid, therefore R will be found out by R1 plus R2 plus R3 upon 3, and then we take the routine calculations with that R. Otherwise, if you want some other specific points, then R need to be interpolated with the help of those shape functions which are already given, and with the help of that we have to calculate that. Once we know how to calculate the, see what is the total size of the element stiffness matrix, you want to tell me? Here again it is going to be, since there are 6 degrees of freedom, it is going to be a 6 by 6 matrix. Like this is going to be 6 by 6 matrix. So now, how to take into account the effect of body force? Only that first part I will show you. The remaining traction and other details we will discuss tomorrow, the next class. Body force term. See, this body force term is 2 pi Fe, okay, integration. Okay, this is the integration over the element Q transpose F into R into dA. And we have already seen that U is nothing but Q and W, and F is nothing but Fr and Fz. Okay. So therefore, accordingly, this will be written as 2 pi integration U into Fr plus W into Fz into R into dA. And since you know U and W in terms of the shape functions, I can write it now. 2 pi over the element E. Yes, what is this U? N1 Q1 plus N2 Q3 plus N3 Q5 into Fr plus N1 Q2 N2 Q4 plus N3 Q6 into Fz into R into dA. Yeah, I am just substituting the value of U and W what we had defined earlier. So now this, after segregating this whole equation will be now converted into this whole thing, whatever we have taken, it is going to be converted into Q transpose Fe, where Fe is the nodal vector, nodal force vector, body force vector. So that is given by, nodal body force vector for every element is given by 2 pi r bar. As I told you, it is to be evaluated at the centroid. So therefore, these are coming Fr bar, Fz bar, Fr bar, Fz bar, Fr bar, Fz bar. So this is what you have to find out. This is the transpose of this will give you the body force, how exactly you are going to get this. So once this is known to you, you can directly take it to the global load vector and you can find out the exact location of the global vector where it is going to be added, and then we can find out the KQ equal to F equation. So with this, let us close today, and in the next class I will be taking about the second force, that is called traction force. How to take into traction. It is very much similar to the CST diagram what you have already done. For CST you have already developed this, but still I would like to show you for even this is over.